tell something about complexity notation, something which we'll be using quite a lot in the following material of the course. So complexity notation is basically used to have an estimation on the growth of functions. We roughly distinguish between three types of functions in at least in this course. These are exponential functions, polynomial functions, and logarithmic functions. It's a kind of the good, the bad, and the ugly. This being the good, the bad, and this is the ugly. Because if you, in terms of scalability, have an exponential function, that's usually never good. But I'll come to that later. So what is an exponential function? Well, it's typically a function in one variable, like this example, f of x is a to the power of x, where a is larger than 1. We usually talk about positive valued functions and positively valued arguments, because the argument usually is the number of elements or the number of processors or something like that. And it doesn't make sense to talk about the negative number of processors, obviously. So this is an exponential function, polynomial function that you have seen before, right? F of x is x to the power of p. And a log function, typically this form where it's either the natural log or the 10 log or whatever log, it doesn't matter, like that. An important concept is dominance of a function. F of x is said to be dominate a function g of x if f of x grows faster than g of x when the argument is getting a higher value, right? That's the basic idea. We use basically three order notations: the theta notation, the big O notation, and the big omega notation. What they essentially mean is that if I say that a function f is in the order theta in the order of g of x, it means that I can find two enclosing functions g which are multiplied by a constant c1 and c2, where f is always in between, right, for every value of x, right, larger than an initial value of say x0. The big O notation is basically just the right hand, right? So it says that the f of x is always smaller than c times g of x, right? So c, g1, c1, c2 are always larger than 0, and x is equal or larger than x, an initial value x0. And the omega notation is the other way around. So this is what we call an upper bound, and this is what we call a lower bound, right? And that's yes?
Well, what you just said about the big O notation is not quite true. It only holds for sufficiently large input values.
Sure. So
not
it's
for every value.
not. It's for a chosen value larger than x0, right? Not for the whole range necessarily. So you pick a value, and if the argument value is larger than that initial value, then it holds, right? So that's basically what it means. Just a simple example, three functions here. The argument is t, right? So this is a simple linear function, a polynomial function, also a polynomial function. And if you draw them here on a graph, you see that A is a line, that these are these curves here, right? These parabolic curves here, and you see three crossing points here of curves, right? At t is 20, t is 40, and t is 45. And you can say some meaningful things about these functions towards one another, depending on the chosen initial value. For instance, you can see, just by observing the graph, that for t larger than 20, tc is in the order of dB in the theta dependence, right, in the order, and that for t larger than 45, this holds, and for t 40, this holds. You can just see that by observing, right? Now you wonder, is there another means of deriving that without looking at the curve? Well, often you can, just by constructing a proof, right? So let's, for instance, take this case, right? How do we prove that this holds for t larger than 20? Well, if we take the quotient of dc and dB, then we just fill in dc, right? dc is, well, what's on the other slide, 25 times t squared divided by this one. If you divide these two terms by t squared, we get this one, and if we get this to infinity, we get approximately 1.25. So from that it holds that dc is always smaller than 1.25 times dB, right? And we observe in the curve that dB is also smaller than dc, right? So then you immediately have your closing bounds from which you conclude that this holds and hence this holds, right? So by taking kind of large steps in the reasoning, you can easily see that this relation between the two functions holds. Now this is just an example. There's a number of properties of functions. If we treat them this way, it always holds that the x to the power a is upper bounded by x to the power b if a is equal or smaller than b, right? So the x to the power b is the upper bound for this one. It holds that the log of x with base e is theta log by base x for all a and b. Also that a to the power x is upper bounded by b to the power x is a smaller than b. So these kind of relations hold and can sometimes be used to easily manipulate formulas, and we see some of them later on. Also, it holds that for any constant, it's upper bounded by 1, right? A constant is, we say, is order 1, right? This seems a little bit strange, but you can prove that for any c by just filling in the definition and choosing appropriate constants, C1 and C constant for that. If f is upper bounded by g, then also it holds that f plus g is upper bounded by g. Or is f is theta related to g, then you can also reverse the argument that g is theta related to f. Right, so you can change the thing. More importantly, if f is upper bounded by g, it follows that g is lower bounded by f. So you can reverse, take the inverse of the function. And of course, you can split this one in the two halves. That if f is theta related to g, then it automatically follows that g lower bounds f, but it also upper bounds f. Sounds a little bit abstract, but it will come to life if we're going to use it for real systems. Well, how can you prove these things? Simple, like take this property, right? Prove that if f is upper bounded by g, then it also holds that f is plus g is upper bounded by g. Well, you just write out the definition. What does this mean? This means this, right? F is smaller or equal than c times g. Now, if we add g to both sides, and g is positive, so we may do that, then this c, we get g out of the brackets, so we get c plus 1, and we substitute it with a new constant, and according to the definition, it's also upper bounded by g. So that's kind of simple analysis. It's in the appendix of the book also, so you can read it if you think you don't understand it quite. This kind of reasoning, right? So this is just something you need to know. Now we go to the material on parallel computers. Right. Something about parallel systems. If we go parallel, the most simplest thing we can do is to normally we have in a computer an instruction issuing unit, which issues the instructions for the functional units to operate on. And the simplest thing is to do is to multiply the active units that do the calculations and let them be subject to the same instruction at the same time. Right? So instead of issue an instruction on a single data item, we issue the instruction on multiple data items. We call that SIMD, single instruction, multiple data. And most computers have some form of processing capabilities in them. But it also holds in a certain sense for single instruction multiple threading. So that instead of a multiple data item, we're talking about multiple threads. And this is dominantly used in classical CPUs, which have single instruction multiple data instruction unit to operate on. And this is dominant technology in GPUs, graphical processing units, which are also heavily used for number crunching applications nowadays, right? And we'll come to that talk to in somewhat more detail. Now, of course, at some point in time, these execution units need to exchange their data. So we need some form of interconnection network, and we're going to talk about interconnection networks and their properties extensively. Now, how does this work? Well, let's take a simple example. We have a program. If b is equal to 0, then C is A. So the A is assigned to C. Else C is equal to A divided by B. But instead of A and B and C being scalars, they are vectors or arrays here. Right? Because we're talking about multiple data units. So if we make a very extreme simple example, the most extreme simple example we can derive is getting two processing elements, numbered 1 and 2. Right? I had a series of them, now I only have 2. The initial values of A and B are the 3, 0, 1, 2, 2, 0. So we see that A here is a vector with 2 elements, right? This is the first element, and this is the second element. So this is not equal. This is not the same variable, right? So this is A1 and A2. If you want to, so basically we're talking about A1 same holds B1, C2, C1, C2. Okay? And this is the PE1, and this is the PE2. So we start with these values, and then the first instruction is issued to both processing elements simultaneously, and that holds this. If B is equal to 0, do this, right? Now this one, B is equal to 0, so this one is operational, and this one, the condition doesn't hold. So this one is idle, so it doesn't participate in the computation. And this is essential, right? That you can selectively exclude processing elements from being executed. Now likewise, of course, in the else part, this one is idle and this one is operational. Right? In this sense, we can operate within a single instruction context to a number of units at the same time, multiplying our computational capabilities to a large extent in this example. Right? So what can we tell about these SIMD and SIMT programming paradigms? So they either operate in a shared address space, like SIMD, or in a distributed address space, like SIMT, right? SIMT can be executed in a shared address space or not, but this one can also execute by having individual threads, each operating on their own data, but being evaluated in a lockstep manner, right? Hence the word single instruction multiple thread. Usually these are embedded in a kind of heterogeneous environment, meaning that we have a general purpose processor plus some accelerator structure, which takes care of the SIMD and SIMT processing. Important is that we have a notion of being able to use or recognize array constructs that we can simultaneously operate on multiple elements at the same time. It's either explicitly being put in by the programmer in the language or not. There are not many sequential languages that have native constructs for multidimensional arrays, right? In C, you can construct an array with more dimensions, but it's not a real array, meaning that it's just a pointer to a linear structure. If you pass, now you could say, what's the difference, right? Well, the main difference is that with an array, you have meta information regarding the dimensions. And this meta information is passed if you pass the data structure as a parameter in a function. Right? So if I put, say, I have a function foo, and I pass a structure here, C or something like that. In C, the meta information is not there. You just pass a pointer, a reference, right? It's lost. So you have to find other ways to doing that. While in Fortran, for instance, an array is a native object, a data object. And the array information is also passed with in the function. So the procedure that is being called, or the function that is being called, can have knowledge about that structure. But for here, it's essential, right, to be operate on array-like structures. So either we have to find them by using compiler technology and recognize. So there are, for instance, what people started to use is they call it vectorizing compilers that try to figure out that you're, instead of being operating on elements, you are using to operate on vectors, right? And it can recognize certain loop construct and change it to vector instructions. Sometimes it's very successful, but not always, right? There are enormous amounts of ways that a programmer can hide from the compiler what he or she is really doing, and in such a way that the compiler cannot recognize the vectors. Or use language extensions. That's another way of expressing that you're working with vectors or arrays. Examples are NVIDIA's CUDA or OpenCL, which is an open language platform for programming these SIMT machines. If we make it a little bit more complicated in terms of parallel machines, we make each processing element slightly more intelligent by giving it its own instruction issuing unit, right? Its own control unit. And then we are talking about multiple instruction, multiple data, because each unit can do its own work on its own data. And of course we need an interconnection network to connect the elements. There are many variants in this. This is a very generic structure, but nothing is being said about how the memory is structured in this picture. And that makes up the major difference in all machine classes. So the most simple structure is what we call the uniform memory access computer, where on the one hand we have these individual processing units with their own instruction units, and on the other hand we have a linearly numbered memory where all processors have equal access to, right? So it doesn't matter when I access the data item from this one or this one, they all access the same memory elements at the same time, so the penalty for them to get a memory element is the same, basically. Now, of course, reality dictates that this is not a very handy construction, because if we really want to be totally fair, then we introduce some delay in the interconnection network, and computers generally don't like that. So what you see in practice is that often each processor has its own cache, right? And to hold all the data and the instruction elements that are frequently used in each processing element. Different model is to go back to this one, to not put the memory element banks here independently, but kind of give them away to the processing elements. So what you do is you retain the global structure, so the memory elements remain numbered from 0 to n, but the banks are divided up and placed more closely to the processor. So now we have that if I have to access a data item which is close to mine, this is way faster than if I access the memory element of this one. But I can still do it, right? So it's still globally addressable. So we classify that as a non-uniform memory access computer. And there are some machines have been built according to this structure. It does imply that we need special hardware to enforce this, right? Because to make this address space uniform is not something you get for free. I mean, the memory arbiter has to decide whether it goes to its own local memory or to the remote memory, and then all these requests have to be serviced. Both UMA and NUMA have in common that they have a called shared address space, right? Shared memory address space, and that read operations are basically not different than if we would have a sequential processor. Write operations, on the other hand, need some form of mutual exclusion, because you might have conflicts of two or more processors wanting to write at the same memory location at the same time. From the programming point of view, this kind of machines can be approached by using thread libraries, like the POSIX library, or maybe a Java thread library or something like that, or by using directives in a programming paradigm. And well known are the OpenMP extensions to C or to Fortran, which enable you to operate in this kind of environment. So there is language support to support this shared address space model. Of course, we can go a very different way. That is to completely decouple the memory structure of each processor, in that each processor has its own memory here, and there's no way I can directly address this memory from this one. So if I have to get data from another processor, I basically have to ask for the memory and the data items to the other processor. And that is what we call a distributed memory architecture. For these kind of systems, the remote memory is only accessible through explicit communication. The typical approaches, what we have, is using a library to be able to exchange messages like MPI, or to use a high-level language, which there are not many of. High-performance Fortran was one we tried to attempt, but it's more or less died, this variant, to automatically generate these kind of messages from a single program. Now it seems to be unhandy to have these two views of the computing world, right? So you might wonder, why have these differences? Does anyone has an answer for that in the room? So on the one hand, this shared memory model, where everybody is working in a shared address space, and this model where this doesn't exist. Yeah.
Well, this seems to me more scalable, as in once the architecture is in place, the hardware is there, you can extend this.
Yes.
But if you have a NUMA architecture, for example, that would be more difficult. But
So why would it be more difficult?
Because it seems to me that it would be integrated hardware, CPU memory, all in one location.
So the complexity is in the hardware.
Yes.
You had another argument for that?
I thought it depends on the computation that you have to do.
Yeah.
You have to choose the communication model then. I mean, it's all about also the application and the platform.
Yeah.
Yeah. Like a big question.
So you said it's depending on what you want to do with the computer, where it is any other. Yeah. So it's also true for some applications. This is not really hurting you, right? For other applications, it does. Yeah. But scalability is one of the major arguments for going for this model, right? You can only work with a shared address space for a limited number of with a limited number of processors, and beyond that, it becomes prohibitively expensive to realize that. And so you see a kind of divide in the world, right? That the relatively small scale systems, say the 4-core or the quad cores you have on a chip, are dominantly shared memory, but the real top of the line systems I've shown you last week are dominantly distributed memory machines, right? There's no escape from that. So they're equally important, serving different worlds, basically. And to make it more complex, these high-end systems often have a combination of these two models, right? So the number of nodes, say 1 million, are basically distributed memory, but a node may contain 8 to 60 processors, which are basically shared memory. So it's kind of hybrid models you can imagine are not the easiest ones to program. So another important thing is how to have a model against which we reflect our parallel algorithm against, right? Because we want to know if it's good, it's already, the arguments start already with a sequential machine. How do we know that we have an efficient algorithm, right? Well, then we need an ideal machine to match our algorithm against and see if we compare this with an ideal machine, we can derive a complexity. If this complexity is good against the ideal model, we have a good sequential algorithm, and the same holds for our parallel world. Now let's step back. You probably already have had that, but if we go to the world of sequential algorithms, we have the notion of the random access machine. Now, what does that hold? Well, it uses a simplified abstraction of the hardware, and you implement an algorithm on this machine, and then usually the execution on a real machine follows the trend using this the complexity analysis for this idealized machine. Right? You can kind of rely on it. For the parallel world, we have something similar, which is called the PRAM model, the parallel RAM model, pronounced as PRAM. And I will show you a little bit the differences between the two. There we use a simplified abstraction of the parallel hardware, and we will see that the gap there is somewhat larger than in the case of the sequential machine. And that makes making our lives a little bit more difficult. Now, how does it work? Well, the RAM model is quite simple. We have kind of a read-only input tape of symbols. We have a write-only output tape of symbols. We have in a memory, a location counter, a very simple machine to execute on. Now, what does it boil down to? Well, we read an input of size n in our calculation. We have constant time instructions, so every instruction we have uses constant time, right? We have a random accessible memory of unbounded size, so no limitations. And the time complexity is simply the number of constant time instructions, right? Symbolically as a function of n. And often we can even simplify it as the number of arithmetic operations. So in that sense, an n by n matrix vector multiply can be, oh, here it's again Microsoft incompatibility for my Mac. it's in the order of n squared operations. Right? So the time complexity of this n matrix multiply is in the order of n squared. Right? Everybody knows what a matrix vector multiplication is. It's quite simple. We can have the same argument about space complexity. There it's just a maximum number of constant size memory locations, also symbolically as a function of it. That's relatively simple, right? So the complexity of an algorithm can be derived from that. Now we can do the same thing in a similar thing in the parallel way. The PRAM model. Here we have something extra. We have a number of these processors, P processors, and now the memory is again of unbounded size that is uniformly accessible by the processors, meaning equal and constant access times. Right? Kind of ideal world. From wherever I access the memory, it's equal time and it's always the same. Right? Processors share the same address space, share memory. Processors have a common clock, meaning that they operate at the same speed. But of course they may execute different constant time instructions, one per clock cycle. And resource contention is absent. Right? There is no, I don't have to wait for another process. Whenever I want to grab something, I can get it at equal and constant time. Then, in that case, the complexity is the number of constant time instructions again by any processor. And if I take my n times n matrix vector multiply, it's lower bounded by log n. Why? Yes?
Doesn't take into account the limitation.
No resource contention. And everything is equal. This is an equal world. Everybody is equal. Nobody is punished. So it doesn't take into account resource contention. So why lower bounded by log n?
Well, didn't you already write it down there? Well,
Where?
it's the simultaneous write operations. Well, the thing is you need to write the result back,
Yeah.
and that will take log n.
Yeah, but you have to do the operations also.
Yeah, but those are, if you have enough processors,
Yeah.
it's pretty much constant time.
Yeah.
So, the dominant factor is the writing.
I would say not the writing, but the operations.
Well, that's what I said. If you have enough processors,
Yeah.
then you just divide it over the processor. So basically it's, what, one arithmetic operation per processor,
Yes.
or at least a constant number.
Yeah.
So that would make those each, constant time.
Yeah. The wide log n.
Right, communicating the results back to wherever it is you need them.
I don't think it's the right back. Yeah.
Aggregation of the results.
Yes, it's the aggregate. Yeah. What do you mean by aggregation?
You have to separate multiplications and additions, and in the end you have to do again an iteration.
You need to collect them back into one coherent data structure.
Yes. Yes.
But the log it comes
If you take the matrix, right?
The logging is because of this notation.
So this is the matrix, and this is the vector, right? So basically what you do is you have to multiply the vector with the rows. Each row is, so multiply the elements and then adding them, right? And the multiplications are independent, right? So you can give them to each processor, but the additions cannot be, right? The addition can only be done in a logarithmic tree. And that's causing the lower bound. So that's the part also you cannot parallelize. Right? So you have the products here, which they need to be summed up, right? Into the final sum and then placed back to the result factor. And that's the logging. What's causing this? So the summation tree, causing the lower bound. But you see, it's a big step, right? Of course, nothing is being said about the delays and of getting the elements together and so on. And but everybody is in the same bandwagon. So if I say equal access, then no contention, then we're all the same and nobody profits, right? So then it's the only thing what counts is the logarithmic summation tree in the end. So you see, this is a kind of ideal result, and in reality, it's difficult to approach this because of all these problems with hidden resource contentions in the system, right? Because in the ideal case, I will never be able to realize, especially the second preliminary, that we have equal and constant access times into the memory. On the other end, it suggests a big step, right? From n squared to log n. So there is some potential that we indeed would be able, if we could build such a computer, could speed up this rather elementary operation, reducing it from a polynomial execution time, right, which is the bad, as I said, right, to the good, right, the logarithmic execution time. So there is some light that this would be possible, but there are a lot of steps in between to take care of, and we'll continue the second hour with these kind of arguments.